All right, welcome. Now it's official. So please set the channel to 41. That's going to be our new channel, hopefully. And press 1 and check that your light blinked green. In that case, you're all set. After that, press 1. Check again that it blinked green. When you press the button number 1, at the same time, you can see if the number changed, probably, if it's right at the same time when you press and the change happens. So probably that's your clicker has been registered. So now I'm going to switch from this slide, and if anybody else coming in and sit down beside you, you should tell that person, change the channel. Now it's 41, press 1, okay? So now it's your responsibility, not mine. Well, when I was watching my lecture, I realized that, well, first of all, when I was doing my first experiment, my hand was blocking the view. So only I could see the numbers, and that made that experiment useless. So I decided to redo it. And when I did my next experiment, trying to use the Skype to project, I realized that instead of hitting live, it was showing a still picture of something else. So it didn't work. So kind of have a question why nobody said anything. And I know why, because the gentleman, 1, 2, 3 in the 4th row, you promised me attendance, and now, so the next step, the next assignment, if anything goes weird, please tell me, okay? All right. So, very quickly. Where is my boundary? This is my boundary, okay. As we know, if we want to move an object which is held by a force of static friction, we have to apply a force which is greater than a certain value, the critical one. So for example, right now, I'm pulling on the string attached to this 5 kilogram weight, exactly the same as last time, and nothing is happening because the force is not strong enough. So I'm pulling, and eventually it starts moving. It starts moving when the force is about 10 newtons. So that means the maximum magnitude of the force of static friction this surface can provide is about 10 newtons. If it's below, it's not moving. It's above, of course, moving. So to make it move, I have to apply a force to it, 10 newtons. So that's what I was doing by attaching this scale to this rod. The force which this scale measures doesn't show the force applied to this, of course. When it starts moving, that means this rod applies the force equals 10. The force which I am applying to the rod is different. And it depends on the location. So, see, it's not 10. It should be much stronger than 10. So when it starts moving, this force equals 10, but not this. And if I move it even further away to generate exactly the same force, 10 newtons, Here, I have to apply much stronger force here. So that's why we said the distance matters. The point of application does matter. And a similar experiment with a string. With a string. And so if the direction is perpendicular to the rod, the direction of the force applied, to achieve 10 newtons here, we apply in practice, well, okay, 16 newtons there. But if now I change the angle to apply the same 10 newtons to this weight now, I have to do a different force, much stronger, because I have to generate the same component of this force, which is supposed to be perpendicular. So this component has to be the same, but because of the angle, this force has to be stronger. That's how it works. And that's why we introduced the definition of the torque as a component of this force times the lever arm, times the distance between the axis of rotation and the point of application. Now, if we talk about this rod, what was my next experiment? Yeah. I wish everything would have been made from gold. I just could retire. So this is the physical axis of rotation. But as we know, when we're calculating torques, we can choose the abstract, the mathematical axis of rotation anywhere. It doesn't have to be here, it doesn't have to be the hinge. It can be anything. So I just can't win, you know, it's either this way or this way. Why is it in equilibrium? Well, because force number one, I just can't win. What smart person invented screensaver without timing? Okay. All those guys, they think they're so smart. Any room for a physics class should have at least 3 different cameras. So when, I don't know, 33 years from now, you are the president of a university, add cameras, please. All right. So force of gravity, hinge force, tension force. And of course, if I want to keep the same balance, but for example, I want to apply a force at a different location, I have to apply a different force. And if I actually, I think I have. Add an additional weight to it, that adds an additional force, which adds an additional torque in general, and that changes everything. It's like fishing. Okay. See? That's the force with the weight. That's the force without weight. If I attach the same weight at a different location, let's say here, that makes a big change, which in the force we have to apply to keep the rod in equilibrium, to keep the net torque be equal to 0 again. And the last one was with the meter stick. That's actually was a problem we wanted to solve, and we will. So something like this, right? Well, of course, now it is also in equilibrium. Yeah? And there is a force of gravity and force here at the pivot. That's not the equilibrium we like. We want when the meter stick is horizontal. It just makes our calculations easier at this point when everything is up or down. Calculations are real straightforward. So, oh, this is what you should look like, the shadow. It's very clear. So what should we relate to describe a situation like that? Well, of course, same parameters. There's a force of gravity here. The force of gravity, well, strictly speaking, we don't know which axis has been chosen to describe this phenomenon. So we have to include the mass of this hanger. There is the mass of this meter stick, which is applied to the middle of the meter stick. And depending on what we're looking for, well, in this problem, we're looking for the mass of this meter stick, so we need to know all distances. We need to know the mass of this weight, which is 100 grams. And then we can set up equations and calculate the mass of this meter stick. And, you know, so to finish all the demonstrations and to make a transition from fun stuff to boring stuff like calculations, I'm going to show you again this. Half of you have seen it already in a lab. Yeah. Should zero it. That's not the right perspective. This is the right perspective. Oh, better. So we have the normal force number one, normal force number two, the force of gravity because of this weight, and the force of gravity acting on this board. That's it. That's all we have. And depending on the situation, for example, like this, yeah? In equilibrium, we can relate all these variables. This reading, which represents the normal force, this reading, which represents this normal force, the force of gravity due to this weight, the force of gravity acting on the weight. Weight is acting on the board, of course, but the force acting from the weight on the board has the same magnitude as the force of gravity acting on this weight. And finally, the force of gravity acting on this board, which applied to the center of this board. So we have free body diagram, and we choose any axis of rotation, and we can solve it. And we can see what's happening if we move the weight one way or another. And if we set, for example, this normal force to 0, that should tell us the location of this weight, the critical location of this weight. So beyond that location, either it topples or we should apply a force down, like we should clamp it up to prevent it from toppling. Any questions? You didn't tell me. Thank you. Why? You said you would do it, so. All right, I guess we don't need it anymore. So this is what I was talking about. You see? No, you can't, because the hand is blocking the scale. All right. And we have one rebellion in this class. I'm not sure it's good or bad. Nobody knows. Yeah. Well, that was the literally last slide we saw on Monday. I asked you, where would you want to choose the axis of rotation, that abstract point relative to which we want to calculate torques? And the number one wins. So let's do this. So I want to choose the axis of rotation here. And relative to this axis, well, the torque due to, well, let's call them force number one, force number two, force number three. The torque due to the first force equals what? Zero. Because this line of action passes the axis. There is no distance. There is no lever arm. So 0 times force, still 0. Now, this force, number two, relative to this axis, generates positive torque. Torque number two is equal to, well, R is 0.2, I use meters, times force. Do we know the magnitude of the force? No, we don't. So we just write a variable which represents that magnitude. And now this force, relative to the same axis, generates a clockwise or negative torque. The torque number three is negative. And it has to be equal to, well, distance, this distance. Can someone tell me the distance from this point to that point? Why? So this is basically, can we read or not, right? So if we can read, a meter means a meter, 100 centimeters, and that's physical fact. The force of gravity should be applied to the center of mass of that meter stick. For the uniform object, it's right in the middle. So this distance is 50, and this remaining part is 10, 30 minus 20. So 50 minus 10 is 40, or 0.4. And now that should be equal to the mass of this meter stick, which we are looking for, times g. And now we can write the torque balance equation. Yeah. T1 plus T2 plus T3 equals 0, or 0 plus 0.2 times F2 minus 0.4 times m times 10 equals 0. One equation, two unknowns. What do? Well, before we only had one option. We could try writing a different equation. And in this situation, that would have been a force balance equation. Two forces are down, one force is up. So F2 minus 0.1 times 10 minus m times 10 equals 0. That's the force balance equation. Force number 2 points up. Two forces of gravity point down. And we could have solved it now because we have a system. Two unknowns, two equations done. But now we also have a different option, which 9 times out of 10 gives the solution faster. Yes? Point 100 grams converted into kilograms. I just did it automatically. You know. And 10 is G. Yes?
Why is torque negative for?
According to the definition. If this is the axis of rotation of our choice for any object, if the force tries to rotate it clockwise, we don't say rotates it because it's actually not moving, it's in equilibrium. But if we had only this force acting on it, in that case, this object would start moving clockwise relative to this axis. We have to imagine that it's nailed at that point. Again, in real life, the pivot is here, but we have to imagine that there is no pivot, that there's a nail right here. And in that case, the motion of this object would have been clockwise. And as we said, clockwise, that immediately means negative. So, there is another option, again, which I recommend trying first, which is choosing a different axis. Because we have a flexibility, we can choose the axis in such a manner so a torque of an unknown force can be eliminated. You see, this torque is equal to 0. And it doesn't matter if we know that this weight equals 100 grams, or it could have been unknown weight, the torque still would have been equal to 0 due to the distance. So now, my question to everyone. How do you want to choose the axis of rotation now? So your torque balance equation would have the torque due to the second force be eliminated, be equal to 0. Eliminated. Laminated, eliminated. You get. And this is probably the most important experience of this whole topic. All right. 5, 4, 3, 2, 1, stop. See? I would do exactly the same thing. Absolutely. I agree with most of you. Because now, if we choose the axis here, we don't really need to know this force anymore to answer the question about the mass of this meter stick. So we have same force as number 1. The force number 1 will be equal to 0.1 of a kilogram times 10 meters per second, so 1 Newton. And the force number 3 will be equal to that unknown mass times 10. And the force number 2 is still unknown, but we don't care anymore. So relative to this new axis, that's my new axis, this torque will be what? Positive or negative? Positive. You see, it's the same force, but a picture behind the torque generated by that force was 0. Now it's positive. This force generates a negative torque. So torque number 1 should be equal to 1 Newton times 20 centimeters, 0.2. So 0.2 Newton meter. Torque number 2 equals 0. Torque number 3 equals, so it has to be negative. It should be equal to force, which is m times g, times this distance now. So distance also changes. It's not 0.4 anymore. That's going to be 0.2. Again, this is a half of a meter minus 30 centimeters. 20 centimeters or 0.2. And if we add them up all together, 0.2 plus 0, well, plus negative m times 10 times 0.2 is 2, should be equal to 0. So m equals 0.2 over 2. Turns out also 0.1. See how the convenient choice of the axis helps. Any questions? And of course, both calculations, both of them illustrate how important is to see the geometry. Because when we need to figure out distances, it's all about geometry. All those distances related purely geometrically, nothing to do from the point of view of physics, right? All right. Well, of course, this theory has a lot of practical application. The easiest one is mechanical advantage. Archimedes said famously, give me a lever, I can move the earth, because he actually invented the mechanical advantage, how it works. This is in a simple illustration. What minimum force should we apply in order to move a very heavy object? Yeah. Or vice versa. So the actual question is, if we applying this force and we can't make any stronger, yeah. So that's the maximum we can generate by our hands. What maximum mass can be moved, can be lifted? Well, all right. That's a very clear situation again. There is a force of gravity action here. M times g, there is applied force, 30 pounds. And we neglect the mass of this lever, so this equals 0. So all we have to do to relate these distances, there is the force, of course, but if we choose the axis here, we are eliminating. Now, what do we eliminate? Do we eliminate the force? No, the force doesn't disappear, it doesn't go away. But the torque becomes 0, because now there is no distance between the line of action of this force and the axis of rotation of our choice. And in this situation, m times g times distance number 1, which is 30 centimeters, should be equal to force, applied force, times distance number 2, if we use magnitudes. That's it. Or we can use pounds, and in that case, the same mass measured in pounds should be equal to 30 pounds, the force we're applying, times with this distance, which is 150 centimeters, divided by this distance, which is 30 centimeters. And now it's an illustration of convenient fact again. Sometimes we don't have to convert things. For example, here centimeters and centimeters getting canceled. The ratio stays the same. 15 over, so that's how heavy it can be, 150 pounds. Now, from the point of view of the reasoning we have to apply to answer any question related to this situation or any question related to that situation, from that point of view, there is no difference. All we have to do is, well, let's do what we have to do. Right? Well, first, of course, we have to draw a free body diagram. So this is a board. First, we have to read very carefully, is it massless? Does it have a mass? If it has a mass, we should, yes, this board is heavy, so we should include immediately the force of gravity acting on the board. Now, there is a fulcrum or pivot here. It provides the normal force. Touching means force. Now, because of this lady, which has a weight, so that's not the mass, that's the force. mg already, 530 newtons. So she's about 53 kilogram weight. So another number, and where else? The bolt. Well, strictly speaking, in general, we don't know the direction of that force. But in our experience, we know that without that bolt, if we cut it, it would start tilting. So the bolt actually prevents it from making rotational motion, which means this force from the bolt should act downward. If we don't know, if we're not sure, we can choose any direction and just stick to that direction. And if in the end we get the positive number for this force, the direction was correctly chosen. If it's a negative number, actual direction should be the opposite to what we thought. Now, distances. The whole length of the board is equal to 3.9 meters. And this distance equals 1.4 meters away from the left. Yes. So what is this distance equal to? A half of 3.9, yes. What did you say? 1.95. Now we are finished with the first step, free body diagram. The next step is, that's the step number one. The next step is what? Someone should say something. Axis. Choose. Well, we can draw x and y axis. We don't use them usually. But we have to choose very clearly. We have to choose very clearly the axis of rotation. That's, again, a fictional point. There is no actual rotation because everything is in equilibrium. We have 4 natural choices. Number 1, number 2, number 3, number 4. Every point of application is a natural choice. But what would be the most convenient choice? Well, it depends on what we're looking for. Find the forces. Okay. So this is the first unknown. This is the second unknown. So the rule of thumb is choose the axis of rotation at the point of application of an unknown force That's it. That's the rule, not the law. Yeah. In that case, we are eliminating one unknown torque. So this is my first possible choice, the axis number one. Relative to this axis, the torque due to bolt equals 0. Any questions on this? The bolt force acts, well, parallel to the line of action, which passes the axis of rotation. There is no r, there is no distance, so it's 0 times the force. That's why it's 0. Now, but what I'm doing now, actually, sorry, the axis, that's my third step. After I choose the axis now, I want to write each torque relative to that axis. That's my torque number one. Torque number two, the normal force. Well, relative to this axis, normal force wants to move it counterclockwise, so that's a positive torque. It has to be equal to 1.4 times the magnitude of the force. 1.4 is the distance from the point of application to the axis. Done. The torque due to gravity, force of gravity acting on the board. First of all, relative to the same axis, it's clockwise, which means its actual value is negative. It has to be equal to this distance, which is 1.95 times the magnitude of the force, which should be equal to 12 kilograms times 9.8 meters per second squared. I round it up. And finally, the torque due to the lady, her weight, again, has to be negative, has to be equal to this distance, which is the length of the whole board. And times the force, which is a given number, 530 newtons. Step number 4, write the torque balance equation. So I'm going to do it here. 0 plus 1.4 times the normal force minus 1.95 times 120 minus 3.9 times 530 equals 0. This is an equation which has only one unknown. You solve it, that immediately gives you the answer. Now you have a fork. To calculate the second unknown force, you can use either the force balance equation, because all forces also cancel each other out, or, as a nice exercise, you can shift the axis. For example, choose it here, the axis prime, all prime, and use the torque balance equation again. I'm not going to do that. That's a good exercise, in addition to your homework assignments. Any questions? Here. Now, I want to talk about the example when we have something angled at a certain angle. Here, we have 1, 2, 3 forces acting on this rod. This rod is suspended, and let's see. If you can do it fast, I will. If not, I'm not going to spend too much time on it. You can think about the question first. Where's the question? Ah, yeah. And you actually can start. Entering your answers. basically something like that. I just want to, what do I need to do? I need to make it easier. So this horizontal torque, horizontal rod. Force number 1, force number 2, force number 3. First of all, what can we notice? Yeah. If we apply the force at a different location, that changes the tension which we should apply to it to keep it horizontal in equilibrium. What else? Oops. If I attach an additional weight to it, or if I just apply an additional force, again, to keep it in equilibrium, accidents happen, especially in physics. But you've noticed, just before it broke, the force which you could read on the scale had a different value. Of course, it has to have a different value if you have an additional torque acting on it. So to balance it out, this force should change. So the most popular answer is number 3, and number 3 is this. So relative to the left end, this is the left end, so we choose the axis here, and the relative to that end, it's counterclockwise, which is positive. Relative to the right end, well, if we choose axis here, now you would have to say 0, because now the same force has no distance at all from the axis of rotation, right? So we can choose any axis, and of course in equilibrium, all the net torque will be 0, and there's this problem which I want to actually do. This is a ladder, and in general there is a person which might walk up or down of this ladder, and if we had no friction at all acting on it, it wouldn't stick. Yeah, it wouldn't be possible to keep it in equilibrium. Well, for example, these wheels are almost frictionless. Oop. These wheels are almost frictionless. So if I have no friction at all, come on. Who broke it? See? You can't make it still. You have to have a friction. Well, so in this situation, the top end is frictionless. In general, there's an additional friction right here, but the bottom end being held by the force of friction. And there is a force of gravity acting on this ladder. And also there might be a person standing on it. So that's an additional force of gravity. And if we walk, and if friction is not strong enough, actually, if you're too high, that might slide. You can die. So every time, calculate what's the maximum height you can actually walk up the ladder. In this situation, we have, well, there is the normal force, and there is a force of static friction, and there is force of gravity, and here there is another normal force. They touch. Even if there is no friction at the top end of the ladder, because they touch each other, the wall of the ladder, the force is not 0. That's what we call the normal force. And that's it. That's free body diagram. That's the first step. Now we have to choose the axis. Well, what we're looking for, this. That's what we want to calculate. Okay, well, so let's choose the axis at the top. Axis at the top end of the ladder in that case. First of all, we need a bigger picture. mg, f normal 1, f normal 2, f normal 1, f friction, my axis. So now torque. The torque, well, from top to bottom, the torque, because of the second normal force, equals 0. That's because we wanted it to be equal to 0. Now, this torque, the torque due to force of gravity acting on the ladder. And now we have to choose. We have 3 expressions for calculating torque. The definition, the second one with the sign, and the third one with the lever arm. I will be using only the last one. So to apply the last expression, first I need to see the line of action. That's the line of action. Now I need to see the lever arm, and that's the shortest distance from the axis of rotation to the line of action. That's the lever arm, LMG. And now it should be equal to mg times this distance. How can I calculate that distance? Very simply, we know that the whole ladder is 2 meters long, which means this equals to a half of that 1 meter, and we know that this angle is 30 degrees, so we can apply, or that angle is 30 degrees, so we can apply our knowledge of right angle triangles, and that should be equal to a half of a meter, sine of 30. So, okay, moving on. The and minus, I'm sorry. That supposed to be a negative torque. Moving on, the torque due to force of normal force number 1. So first of all, that's the line of action, and relative to my axis, it wants to turn the ladder counterclockwise, so it has to be positive. It has to be equal to the force times the lever arm. What is a lever arm? Well, again, first we need to draw the line of action of this force. That's the blue line. Now we need to draw a perpendicular which starts at the axis of rotation and which ends at the line of action. This green line now represents the lever arm of this force. What is it equal to? Again, we have to solve a right angle triangle. We have, you didn't hear that. Me too. I just want to finish torques because we have left only one. And now the torque due to frictional force. How? First of all, positive or negative? Well, it points like this. That's the line of action. So relative to the same axis, it wants to make it move clockwise. That makes it negative. Negative. It has to be equal to this magnitude of the force times, well, the lever arm And now, to see the lever arm, we have to draw a perpendicular which starts at the axis of rotation and which ends at the line of action of this force. So this is what we call the lever arm of force of friction. What is it equal to? Well, that's the same triangle, the hypotenuse, the angle, so that's supposed to be equal to hypotenuse times cosine of 30. And the last step is to say that the net torque equals 0. And now you just have to solve it. You may add an additional equation. Yeah, you can choose the axis at a different location. You can cancel all forces in a vertical direction, all forces in a horizontal direction. Well, thank you very much. We are done with static equilibrium. Well, I'm done. You're not. You're still going to do a lab and a discussion. So the sign-in sheet is here for anyone who still needs it. And I'll see you on Friday. Yes. Where or what? The shortest distance from the axis of rotation to the line of action.
And what purpose? I didn't understand the purpose. I mean, obviously it made...
The purpose of it to calculate torque.
So is that sort of, it's acting as a distance?
It is a distance. Yeah, the lever arm
So it's the distance for the torque formula.
is the shortest distance from the axis of rotation to the line of action.
Okay. And we need...
The lever arm is the shortest distance from the axis of rotation to the line of action. If you multiply the magnitude of the force by its lever arm, that gives you magnitude of the torque. You should check slides from the last lecture, because we started from one expression for the torque and moved on to second, and then we moved on to the third one. And the last one is what I'm using. Yes.
What does how can I calculate FM1?
How can you calculate the lever arm?
The FM1, this one.
Well, at this point you can't yet.
So what does the note mean? I see something like...
Well, at this point you still can't calculate, because the equation which I have, only one equation, which has two unknowns.
Yeah.
Two unknowns.
Yeah.
So we need an additional equation. You have to write an additional equation. And to write another equation, you have two options. Mm-hmm. Number one, you can choose another axis of rotation, which I would suggest. Or number two, you can balance out all the forces, because forces, well, net force also has to be equal to 0.
Right. Okay.
So maybe I will spend some more time to finish this
Okay.
on Friday, okay?
Okay. Thank you.
But you should try it at home.
Just curious,
Yes.
is there lab next week because of the exam? Because I know there wasn't for the first exam, but I saw the email that we changed rooms, so I was just curious.
Yes, there is a lab next.
Okay, and it is in the different room for everybody? For like the whole week?
For the whole week, it's going to be in a different room.
Okay.
For the whole week, it's going to be in a different
Okay.
room.
Thank you.
Yeah. Yeah. This is done, so we can unplug this, we can unplug this. We can unplug all this stuff.